Aqueous Equilibria, pages 260 to 266. This is going to focus on titrations. So all titrations are based on an acid-base reaction where there's a neutralization. And if we deal with a strong acid and a strong base, you're always going to yield salt and water. And they're going to actually very perfectly neutralize one another. The base will provide hydroxide, the acid will provide hydrogen, and when those two get together, we make water. So a strong acid, strong base titration, suppose we have a base with unknown concentration that we wish to determine. The unknown concentration can be determined by a process called titration. An acid of known concentration is added to the base until the base is completely neutralized. Using the volume of added acid, the concentration of the base can be found. So if you don't know the molarity of an acid or a base, but you do know the molarity of the other, for example, if I happen to know the molarity of the base, but I don't know the molarity of the acid, then you can do the titration where you figure out what volumes neutralize one another. So for example, if I use 15 milliliters of the base, then if we can find out what volume of the acid could neutralize it, let's say it took 25 milliliters to neutralize it, then we can actually calculate what was the molarity of the acid. The equivalence point is the point where the moles of acid has exactly neutralized the moles of base. So moles of acid equals moles of base. The end point is the estimate of the equivalence point as determined by a dye indicator or some other means such as a pH meter. A dye indicator is chosen to undergo a rapid color change in the region of the equivalence point. The dye indicator only gives an approximate measurement of the equivalence point. So here would be a graph of a strong acid-base titration. And because the graph starts at a pH of 13, I know that it started out with base, and I started adding acid to the base. As I added the acid to the base, notice the pH takes a little bit of time, but once you start neutralizing most of the hydroxide present, then all of a sudden there's a quick drop. And this would be the point at which the indicator would change color in its interval range. So here is where the equivalence point is, which is at pH of 7, because anytime a strong acid is titrated with a strong base, the equivalence point is at a pH of 7 exactly, where moles of acid is equal to moles of base. Notice as you continue adding acid, then eventually we get past the equivalence point, and now the solution is becoming acidic because now I have a greater amount of acid than I do anything else. Acid-base titrations are based on the following acid-base neutralization reaction. You have a strong acid plus a strong base, and then all of it reacts completely to form salt and water, and this is a neutral salt. So you have a completely neutral solution at the end, which is a pH equal to 7 at the equivalence point. For a strong acid-base titration, the products of the titration are neutral, so the pH equals 7 at the equivalence point. pH equals 7 for strong acid-base titrations only. Now we'll focus on weak acid and weak base titrations. When the unknown sample is a weak acid, the equivalence point has a basic pH that's greater than 7. Here's an example of a weak acid titration. So notice you're going to have hydrofluoric acid, which is the weak acid, plus sodium hydroxide, which is a strong base. And we're going to yield sodium fluoride plus water. Remember that sodium is a spectator ion, so really we're looking at hydrofluoric acid plus hydroxide yields fluoride, plus H2O. So really that's the equation, the net equation that we care about. The pH is going to be based on our products, and because fluoride is an anion that came from hydrofluoric acid, which is a weak acid, that makes this a weak base, which means that the conjugate is going to be, this is going to be responsible for the fact that the pH is a little bit greater than 7, because that is a weak base and water is neutral, it's water. So at the equivalence point, the titration neutralizes all of the weak acid, hydrofluoric acid, converting it to fluoride. The pH is determined by the fluoride produced by the titration. The conjugate base fluoride is a moderately weak base, which reacts to produce hydroxide, making the equivalence point basic. So in other words, if I take this fluoride and I look at it after I place it in water on its own, you end up getting water transfers a hydrogen over, hydrofluoric acid, and hydroxide. And it's the fact that you end up with the hydroxide that means that we end up at the basic pH. So weak acid, strong base titration. You have a weak acid plus a strong base, and then when they react, you're going to get sodium spectator ion, fluoride, which is a weak base, plus water. And we know that fluoride is a weak base because when we place the weak base in water, then we're going to get hydrofluoric acid and hydroxide in a state of equilibrium back and forth. And so this would be fluoride is responsible for the basic equivalence point because it yields hydroxide while it's in water. Four weak bases titrated with strong acids. A similar process creates an acidic equivalence point. In the titration shown below, the pH at the equivalence point is determined by the weak conjugate acid, ammonium, produced by the titration. This equivalence point will have an acidic pH. So you have a weak base with a strong acid titration. So here's my strong acid, hydrochloric acid, and here's my weak base, ammonia. And then when you transfer the hydrogen over to the ammonia, we get ammonium, which is a weak acid, which if you place it in water, you get ammonia and the hydronium, and it's because of the hydronium that this is considered a weak acid. And you get the chloride spectator ion. So the equivalence point of a weak base titrated with a strong acid is going to be acidic, less than a pH of 7. So finding pKa and pKb from titration data. The hydrogen concentration of a weak acid here can be found from the equilibrium calculation, seen here, making the approximation that hydrofluoric acid minus the hydrogen is pretty much just hydrofluoric acid, so giving us this general equation. When the titration is only halfway to the equivalence point, half of the hydrofluoric acid has been converted to fluoride. So there's something significant about being halfway to the equivalence point of a weak acid strong base titration or a strong acid weak base titration. So the remaining hydrofluoric concentration is the same as the fluoride concentration. Therefore, F minus and HF terms cancel, and this gives us this equation here, that halfway to the equivalence point, the hydrogen ion concentration is going to be the same value as the Ka, and the pH is going to equal the pKa. This gives the equations which relate the pKa of the weak acid to the pH at the point where 50% of the weak acid has been titrated. The volume of base added to this point is halfway to the equivalence point. A similar equation can be found for the titration of a weak base. The hydroxide concentration of a weak base, so ammonia plus water yields ammonium plus hydroxide, can be found by this similar equation. Halfway to the equivalence point, where ammonia is equal to ammonium, the equilibrium equation becomes the hydroxide ion concentration is going to be equal to the Kb, and the pOH will be equal to the pKb. Now we're going to look at some graphs, and you're going to want to make sure that you're familiar with them and be able to generally sketch them. So here you have a pH on the y-axis, and you have volume of acid added. Because we start off as a high pH, that means that we start off with a strong base. The strong base is titrated with a strong acid. So it stays relatively flat, kind of just generally moving downward, but then all of a sudden we have this steep drop, and then this is where the equivalence point happens. And this is the point where the pH is equal to 7. And then after we get to the bottom of the steep drop, then you notice that the pH gets a little bit more acidic as we keep going and adding more acid. A strong acid titrated with a strong base is going to start with an acidic pH down here, again mostly flatline, and then all of a sudden there's a steep rise upward, and you'll notice it's practically vertical here, and then the equivalence point is at 7, so you would actually draw a point or a dot right there to signify that. And then as we continue to add strong base, then the pH begins to increase up here. Now, a weak acid titrated with a strong base, such as hydrofluoric acid plus sodium hydroxide, which yields water plus the sodium spectator ion, and more importantly, fluoride, which is a weak base, weak conjugate base. This is responsible for the equivalence point being basic here. So notice that this is the equivalence point, and it's at a pH between 9 and 10 roughly. So we started with our weak acid. So we have an acidic pH, and this is identified as the halfway point between the starting point and where there's the steep rise in the curve. So this halfway point is where 50% of the acid has been neutralized. And so this is where the pKa equals the pH, or the Ka value is equal to the hydrogen ion concentration. This will be important, and you'll be asked to calculate this. Then, all of a sudden, there's this big jump or rise, and this is going to be the equivalence point. And again, it has a pH that is basic because of the conjugate base being responsible for the pH here. And then as we keep adding the base, then all of a sudden it plateaus up here as a basic pH. A weak base titrated with a strong acid. So here you start off with a basic pH at the top, and then notice when we get halfway from the starting point to where the steep drop happens, this is that 50% mark where the pKb is equal to the pOH, or the Kb is equal to the hydroxide concentration. As we have our little drop here, then this midpoint is the equivalence point, which you'll notice is acidic. It is below a pH of 7, and that's because the conjugate acid, the ammonium ion, is responsible for this acidic endpoint or equivalence point. And then as we continue to add acid, strong acid, it does drop the pH and then eventually plateaus down here. We're going to have 3 note cards now. The first one is for strong acid and strong base titration. The equivalence point is when the moles of acid is equal to the moles of base. The end point is the point where the indicator changes color. That's going to be true for all the titrations. But at the equivalence point for a strong acid and strong base, the pH is 7. This is what the graph looks like if you start out with base and you're adding acid. So it starts at a basic pH. The equivalence point here is pH of 7, and then it tapers off in an acidic pH. Over here, if you start with an acid and you add base, then it's going to start out acidic, equivalence point at a pH of 7, and then it's going to taper off up here around a basic pH. For a strong acid and a weak base titration, we're going to have the weak base, B, plus the strong acid, HA, and the hydrogen is going to transfer over to the weak base, giving us this conjugate acid, BH+, and the neutral anion from the strong acid. It's this conjugate acid that is responsible for the pH being less than 7 at the equivalence point, and it's because the conjugate acid reacts with water to yield the base plus the hydronium, and so that's why it's considered an acid. The halfway point to the equivalence point is where the Kb is going to equal the hydroxide concentration, or the pKb equals the pOH. So here's where we start. This is the halfway point, and so the pKb equals the pOH. And then as we come down here to the equivalence point, notice that it's going to be less than 7 because of the conjugate acid. And then as we continue to add acid, it tapers off down here. Lastly, here's a weak acid and strong base titration. So here's your weak acid, HA, and my strong base, a metal hydroxide, yields. We're going to have the metal ions, which are neutral. We're going to have the anions and water. The hydrogen and hydroxide make water, and then these two remain separate. This is a neutral ion, but this anion, because that's a weak acid, that makes this a weak conjugate base. That's going to be responsible for the pH being greater than 7 at the equivalence point, because this weak base reacts with water to yield the weak acid plus hydroxide ions. Halfway to the equivalence point, the hydrogen concentration equals the Ka, and the pH is equal to the pKa. So that would be here is the halfway point, where the pKa and the pH are the same. And then when we get to the equivalence point, notice it's a little greater than 7, and then it tapers off up here. And of course, this would be if we started out with an acid and we are titrating it with the strong base, adding strong base.